Very happy to be here today. Thanks for the invitation. This is joint work with many people. I'll describe the collaborations that I've had throughout the course of this work as they come up in the talk as well. Before I get into the meat of today's talk, what I want to talk about just more generally is the type of problems that I work on and the way that I approach my research. Generally speaking, I work on problems that I like to call network operations and network security. That, broadly speaking, is working on developing tools, techniques, algorithms to help people run communications networks better in the face of faults, misconfiguration, and malice. Now, I look to particular types of problems to solve in this area. I draw on domains or on aspects of the domain where people really live in the trenches. In particular, I look to network operators and people who work on these problems day to day to really develop a deep understanding of how networks really do and don't work in the wild, and how adversaries tend to operate in these contexts as well. So I work very closely with people in the trenches to identify practical problems where there's some underlying hard question that we can solve. Having identified that question, what I then like to do is apply different techniques across many different aspects of computer science to reduce those messy real-world problems to something that is more easy for us to model or understand. And I'll describe both in the work that I'll talk about today and also in other problems that I work on how I do that across different areas of computer science. Having reduced these messy problems to things we can better understand and bring different aspects of computer science to bear, then try to come up with a solution, but also bring it back to practice, right? Engage with industry, operators, vendors in the real world, and try to take the things that we've developed in the research lab and make them real. And I'll point that out as we go in various parts of the talk. And I'll also talk towards the end of the talk about other problems that I'm looking at where this general method of problem solving comes to light. So before I go further, I just want to sort of focus in on the particular question that I'm going to focus on in today's talk, and that's how we retain the openness of the internet, which in some sense is a fundamental tenet of its design, when on the flip side, attackers are also trying to take advantage of that openness. And I'll talk about that specifically in the context of several different problems. I also work on several other kinds of bigger, hard questions as well, and towards the end of the talk, I'll speak about some of these others that I've listed out here on the slide. So as I mentioned, once I've identified some hard problem to work on, I look to many areas or other areas of computer science to try to develop solutions to those problems. And in today's talk, you'll see elements of security, of machine learning, maybe a little bit of theory and a little bit of policy in the types of solutions that you'll see to the problems that I'll talk about today. And towards the end of the talk, I'll talk about sort of where I'm going with my research and how I hope to, and how I'm already engaging other areas of computer science and the type of work and the types of problems that I work on as well. So what's interesting about the problems that I'm going to talk about today is that adversaries are quite creative and smart, and obviously there are a lot of smart people in the real world who are trying to work on these problems that we'll talk about, but we can engage with these adversaries using many tools and techniques from computer science as well, and we're going to use those techniques in our arsenal to sort of take back control in many aspects of internet communications. So coming to the central question of today, balancing the openness of the internet design with our desire to keep it secure, let me just sort of speak a little bit more about the internet design philosophy, right? And this is a quote I took from a New York Times article from the director of the Media Lab, and I think he put it very nicely, actually, in terms of defining what the internet's design means in terms of openness. So he says, everyone should have the freedom to connect, to innovate, and to program without asking anyone else's permission. The internet isn't centrally controlled, and the assets of the internet are widely distributed. So that sort of fundamental tenet has really been a huge boon to the internet's success, right? This openness, in many ways, has catalyzed growth and innovation. We're seeing, many more users come onto the internet, using it in many different types of, in many different contexts, in many different geographies, and also on many different types of devices. right? So we're seeing innovation at just an amazing pace. So that's the plus side. But the flip side of this, and something that I'm going to focus a lot on today in today's talk, is how this openness also has a downside, which is that it facilitates abuse and manipulation. Right? So we have this tension here. On the one side, openness is good. On the flip side, though, it can be abused. So how do we retain the Internet's open design while still keeping it secure against these parties who would wish to abuse it for their own gain? I'm going to talk about this bigger question in the context of several problems. And the first one I'm going to talk about is how we secure communications on the Internet. In particular, I'm going to talk about email spam. So you may or may not know that about 95% of email traffic on the Internet is spam. That's one problem that we'll try to address in today's work. And I'll focus a large portion of the talk on that particular problem. The other thing that I'll talk about a fair bit in today's talk is censorship. So you may or may not know that about 60 countries around the world control or censor Internet communications in some form. So on the flip side, how do we work within that context to try to maintain, or in some cases, create openness where it doesn't exist in today's communications networks? Finally, and this is where I think I see some of this field going in terms of control, is today when we talk about censorship, we think about hard constraints. Either I can communicate or I can't. Well, 10 years from now, I would posit that when we talk about the Iranian election or the like, that we won't read about Twitter being blocked at all. We'll read instead about the Iranian government using Twitter to manipulate an election, right? So moving from sort of hard censorship to sort of questions of softer censorship or manipulation, I think is where I see that aspect, that part of the field going. And I'm talking a little bit towards the end of the talk about types of things that we can do in light of those emerging threats. So let's jump into the first part of the talk, which is message abuse and spam filtering. So you might think, isn't this a solved problem? I don't see much spam in my email inbox. And you might not see much of it anymore, but the people who do see it actually still see a lot of it. The people who see a lot of it are the mail service providers, the network operators, the people who are making sure that you don't see it, right? So, and they have a huge job cut out for them, which is to make sure that you don't see it. In light of the fact that there's a significant amount, or significant fraction of email traffic that is spam, and the fact that a lot of it does contain these targeted attacks. For example, there's something like 30 to 50,000 unique phishing attacks in any given month. So what do we do about this, right? The general approach and the sort of obvious thing, right, is, well, let's design a filter, right? Sounds good. How do we do that? Well, there are many ways that you can do that. The key question, of course, is what features best differentiate the good stuff from the bad stuff? And this is an age-old problem. Many people have tried different types of techniques to do this. I'll talk about two existing techniques. One is that you could look at the content of the mail. You could say, look at what's being said in the mail and try to figure out, is this something that a legitimate user would say, or is this something that that a spammer might say? So there's one wrinkle to that, which is that if you talk to people who work at, say, Yahoo or Microsoft or Google about mail abuse, they'll tell you something like they've seen 90 to 100,000 different ways of spelling Viagra, right? So in light of that, keeping content filters up to date in the presence of attackers who are increasingly agile at evading these filters is actually an asymmetric battle. I'll give you some more examples on the next slide. The other approach that one can take is to try to form reputations about the sender, right? So you can look at the IP address of who's sending you the mail, right, and try to figure out, is that IP address someone who might be good or someone who might be bad? And there are various drawbacks to that as well, which I'll also point out in just a minute. What we do is something that's complementary to that, which is to say, rather than looking at what's being said or who's saying it, what if we did something like look at how things are being said, right? Who's sending, how are the messages being sent? At what time? Where are they coming from? Where are they going to? What networks are they coming from? Are they coming from regions of the network that, that one could label as bad, potentially? What time of day are they being sent at? Those types of questions. I won't show you all the details of the types of things we look at, but when I get to that part of the talk, I'll show you a few things that are kind of interesting and surprising and worked well. First, let me sort of give you a flavor for why these two existing approaches leave some room for improvement. So as I mentioned, the first approach is to design a content filter, and here's some examples of ways that spam shows up in different shapes and sizes and forms. So here's an example of a spam message appearing as a PDF, right? One that might be attached as an Excel spreadsheet, another one that's sort of embedded in an image. We've even seen spam that appears as MP3 attachments, right? So what's the point here? The point is that it's relatively easy for an attacker to design a new, to embed their message in a new cover, a new cover medium. But on the flip side, as filter designers, for every new cover medium that shows up, they've got to design a completely new filter, right? So it's an asymmetric battle that that is sort of a cat and mouse game where the spammer is likely to always be able to stay ahead. Another place that I mentioned, or another approach that I mentioned, is to look at the reputation of the IP address of the sender. Now, the problem that occurs here, and it comes back to that sort of fundamental tension between openness and security, is that again, keeping an IP reputation list up to date is actually pretty tough because the IP addresses of the senders keep changing, right? And that can happen for good reasons and bad reasons, right? So bad reasons include new infections. A good reason might be you just started up a mail server or you renumbered your mail server, right? The problem here is that the cost of mistakenly classifying a good mail server that you just set up as a spammer is incredibly high because it goes back to that, it violates that goal that we have of openness. So the challenge here is that because the IP addresses of the senders keep changing, right, and this is actually something that we measured empirically, on any given day we saw about 10% of the spam senders coming from IP addresses that we'd never seen before. Right? Keeping that list up to date is actually incredibly tough. So what we propose, is, as I mentioned, is to sort of take a behavioral approach. And here we're going to look at network-level behavior in particular to try to distinguish good from bad. Well, that sounds nice in practice, but how do we sort of make that real? Well, here I'm going to go back to what I showed you on that first slide, right? Is we need some domain knowledge. We need some deep understanding of what spammers are actually doing, right? And we watched them for a while, and we pulled out certain features, right, that are characteristic of spamming behavior that we thought might differ from legitimate behavior. And I'm going to show you some things that we did based on each of these sort of what I call behavioral axioms. So in other words, what's different about the spammers from legitimate senders? The first is agility. In other words, spammers have to keep moving, right? Otherwise, they're going to end up on a blacklist or they're going to be shut down, right? So on the one hand, that's annoying, right? Because the blacklist keeps getting out of date. But wait a minute. They have to keep moving. That's always going to be true. So if we could somehow figure out the way in which they move, right, and look at those movements and how they might differ from those of, say, the way a legitimate service might move around on the internet, then we can use that to our advantage. The other is that the behavior fundamentally differs from, the second is that the behavior fundamentally differs from the way that you or I would send messages, and I'll show you a couple examples of that. Now the third, as we know, is that to be effective, spammers often have to use large networks of compromised machines to both send spam and to do other things, which I'll show you an interesting other thing that we saw later in the talk. But just to sort of speak about it generally right now, because spammers are operating from large armies of compromised machines, often what we call botnets, right? Well, on the one hand, again, that's annoying because they're everywhere. But on the other hand, we can pull out coordinated activity that would not appear just sort of in the context of legitimate network behavior. So we're going to look for coordinated activity, and the way that we can do that actually is to apply machine learning and specifically clustering techniques. So I'll show you that when we come to it. So I'm going to show you just a taste of the types of things that we've worked on and sort of building on each of these axioms. In the first, I'm going to show you some examples of agility that we saw. In the second case, I'm going to show you a couple features that we put into a supervised learning classifier that allowed us to build a spam filter based on network behavior that worked quite well. And in the third case, I'm going to show you another sort of surprising behavior that we observed where spammers actually behave like one another, that actually, when we applied clustering, it actually allowed us to detect something that ordinarily we wouldn't have otherwise seen. So let's first take a look at agility in terms of a particular facet of the internet called the Border Gateway Protocol, or maybe affectionately or disdainfully, depending on who you are, BGP. So if you don't know what BGP is, it's the routing protocol that ISPs use to exchange reachability information with one another. So it's a way that one internet service provider says, here's how, to the rest of the world, here is how you can reach this range of internet addresses. Okay, so here's the first surprise that we saw when we basically asked the question, what happens if we look at spam coming into a particular set of email addresses or a domain, and we look at the internet's routing table at the same time? So here's the first thing we saw that was kind of interesting, was this is a time series plot. And I've sort of sketched out a 10-minute window here between the red dot, which is where an internet service provider said, here is a range of internet addresses that I own, that you can reach through me. Right? And the blue dot is actually a retraction of that same statement, or that same assertion. So already this is really weird, right? Because when you think about running a network, you generally like the addresses to be reachable for long periods of time. And already we're seeing something quite strange, which is, here's a network that appeared for 10 minutes. Right? Okay, so that's interesting by itself. The next thing we see, these green dots up here, and there are 5 of them in this particular case. Those are instances for when we watched for spam arriving at what I call a spam honeypot or a spam trap. We see spam coming in from IP addresses contained within that IP address range. It was only there for 10 minutes. Okay, so that's pretty weird already. So again, this is something that we can use to our advantage. I won't get into the details there, but if we look for these short-lived routing messages, right, that's an example of agility, right, that we can then turn on its head to say, hey, this is really weird. We can use this as an input to a detector. But there's another surprising thing here, which is that if I sort of gave you the task of, go steal a network on the internet, right? Go hijack some IP address space. Would you try to steal a small network or a big one? Right? And we thought, well, probably you'd want to steal a small network, right? Because no one's going to notice if you just carve off a little chunk of the internet. Actually, we saw the opposite. We saw attackers stealing 1/256th of all internet address space in many cases on a regular basis. And then you might think, this is crazy. Someone's obviously going to notice this, right? But actually, it's the opposite. If you think about the way internet routing works, right, it works on something called longest prefix match. And what that means is that within these ranges of addresses, if there's another network or another ISP that's already using that space, then this stolen announcement is going to lose, right? The other routers are just going to pay attention to the more specific announcement. But anything that no one else has already sucked up suddenly becomes owned by the attacker, if you will. And they get a fairly large set of addresses from which they can sort of jump around in. And they've got a fairly big prefix, which means it's less likely to be filtered. Right? In particular, in these cases, we saw large prefixes that were already allocated to a regional registry. So they just sailed right on through. So that's one example of agility that we saw. Another thing that appears is something called, it's often called fast flux. And this is something that a figure that I borrowed from the HoneyNet project that I think describes the behavior quite well. The principle here is that when someone sends you a spam message, often they want you to do something. Click on a link in particular to say, give them your username and password or bank account information or credit card information or buy something, for example. And that site that you go to has to be hosted somewhere. Well, that's got to move around too, right? Because if that site stays in one place for too long, then it gets shut down, right? So you might think again, well, that's kind of annoying. We've got to somehow keep up with wherever that site happens to be hosted. But we can use this to our advantage too, because these things are going to move around. So essentially what happens here is that this is a client here issuing a DNS lookup, and what the attacker does here in step 4, where the name gets mapped down to an IP address, the attacker can keep changing that, right? The first step there would be, Okay, yes, but we can identify these, these boxes at the top. We can identify that infrastructure and go shut that down. Well, the next step is the attacker turns that into a botnet, right? And that starts to move around. So these things up here, what I'm going to show you, these are called authoritative name servers, right? And it's typically not the case that in a legitimately run network, those things move around very much. In other words, you don't see these things being shuffled around a botnet very often. But we see it all the time when we look for this in scam domains. So what I'm showing you here is a cumulative distribution function of the time between changes to that stuff that was at the top of that hierarchy, in particular these authoritative name servers. The red line is bad domains, and the blue line is legitimate domains. And what you see, just to cut to the chase, is that in about 40% of cases for these domains that show up in our spam trap, right, we see those authoritative name servers changing about once every 6 hours, right? So that's sort of like core, name resolution infrastructure for a domain that in any normal case you would never expect to see changing. But in these bad cases, you see it moving all the time. So we can use that to our advantage. Another thing that attackers actually have to do, right, because you can think about the domain name itself, well, that's going to end up on a blacklist too, right? So the other thing that attackers have to do to remain agile is continually register new domains. Okay, so that's annoying as well, right? So you've got to keep a blacklist up to date as attackers register new domains. But wait, right? We can do something cool there as well. What happens when you register a new domain? Well, typically nothing. Nobody looks it up, right? But in the case of an attacker's domain, everybody's looking it up because it's either compromised machines who are looking up that domain, because they're trying to talk to a command center, or it's, people like you and me who have clicked on a link, for a newly registered domain as part of a spam campaign. So basically, what I'm showing you here is the number of distinct networks or /24 networks that look up a domain within the first week of it being registered. And you can actually see, again, sort of to sort of cut to the chase of how to read this, in about 40% of cases, you see at least a few hundred distinct /24 networks look up a bad domain almost immediately. And you never see that happen in the case of legitimate domains, or very rarely. So that's some examples of the way that attackers exhibit agility and how we can use that to our advantage to design more intelligent detection mechanisms. I'll talk about the second axiom a little bit now as well. And here, yes?
Just a quick question
yes.
Before you move on. So this is very interesting. For all these different graphs that you're showing us, where did the data come from?
Good question. A variety of places. So this gives me an opportunity to sort of describe some of our collaboration. So in all of the cases that I've shown so far, except for this very last one, these are things that we've collected ourselves. So I've set up infrastructure to, say, collect spam data, to collect BGP data, and we can watch those. In this case, where we're looking for changes in records, we basically use the domains coming into our spam trap, and then we use those to trigger lookups ourselves. So we can repeatedly ask, where is this domain being hosted? Where is it being hosted? We do that every 5 minutes, and we track changes. This comes actually, I'm glad you asked, because this comes, again, to the kind of style of work that I like to do, which is start by getting into the trenches myself, and then after we did this work, VeriSign said, hey, this is quite interesting. Are there other things you can tell us? And that's what we did over here on the right. This is some work we did with VeriSign. That data happens to be lookups to all the .com and .net second-level domains that only VeriSign can see. So that work we did in collaboration with VeriSign. So this is the type of thing that I like to do, is actually try to find something interesting by building out infrastructure myself, getting people in industry interested enough in the problem to give us data, tell us more about the problems that they have, and then work with them together to do something real. So yes, thanks for asking. And actually that segues nicely into the next part of the talk, because this is something actually that we did with McAfee, who was then Secure Computing. And that's where some of this data actually came from. In particular, the problem that we look at here is what types of behaviors arise or what types of behaviors do spammers exhibit that differ from legitimate senders? And here, again, we spent a lot of time just sort of looking at data to try to figure out, how these things, how the behaviors might differ. And eventually we work with people in machine learning to build a classifier that works. And I'll show you sort of the upshot of that. But I'll focus just now on a couple behaviors that were particularly interesting. There's some obvious ones that I'll skip, so I'm just going to sort of show you a couple highlights. One is you can look at, for example, the distance that a message travels. This is an interesting feature, actually, because in both of the features that I'm going to show you, they're both interesting because you don't actually have to look at the content of the message to actually figure this out. How do we do this? Well, we basically can say, what's the source and destination IP address of that message, right? We can look at, say, the first packet of the connection and figure out where is it coming from and where is it going to. And then we can, with the help of IP to geographic mapping, we can say, how far is that message traveling, right? And what actually pops out, and this, I should mention, is work that we did with folks at Secure Computing. So this data comes from about 8,000 different enterprise networks scattered around the world from the spam filtering appliances that they've deployed in those networks, plus with the help of some people who've helped to label some of that data as well. So we can take the labeled data and say, what's different about the spam versus the ham, if you will, the good stuff. And what we can see here, this is a CDF, and you can see that legitimate mail exhibits a lot more locality, right? So you can see, for example, that in the case of certain spam, which is the red line, the x-axis, I should say, is distance in miles, and if you go all the way out to the far right, that's half the circumference of the Earth. So you can kind of see that the spam is more uniformly distributed in terms of where any particular IP address targets. It effectively spreads out in a more uniform kind of fashion. And the legitimate senders exhibit a lot more locality. So that's something that kind of pops out of behavior. Here's another one that I think is particularly interesting because it comes back to our requiring an understanding of how spammers operate. So if you sort of read about the way these guys work, is they tend to compromise a bunch of machines and then send spam from those compromised machines. Well, what's interesting about that? Well, compromised machines tend to live together in certain parts of IP address space, right? You'll have an enterprise network or a bunch of machines from a broadband service provider, all in one region of space that maybe all have a similar vulnerability, right? Well, so then they've got a bunch of compromised machines from a small portion of the network that can be used to send spam. We can use that to our advantage too. How likely is it that you see a legitimate network, say of 256 addresses, where you see 200 mail servers? Pretty much never. How often do you see that in the case where you've got spammers operating? Actually, somewhat frequently, right? It's not uncommon for us to see networks where every machine on the network is compromised because it had the same vulnerability, and they're all sending out trickles of spam. So we can use that to our advantage as well. What we can do is say, ask, what's the density of email sending activity in any region of space? And the way that this was actually something that we worked pretty hard on with the machine learning folks in terms of how to actually represent this feature, right? Because the intuition is obvious, but after you think about it. But then it turns out that the right way to represent this in a way that classifiers work well is to say, take a particular IP address and then say, how far out in IP address space do I need to go to capture the k nearest senders? Right? So the x-axis here is k, right? And the y-axis here is how far out I need to go in IP address space to get that k. So closer to the bottom here is more dense. What you can see in this case is that in the case of spammers, the k nearest senders are an order of magnitude closer in IP address space. So that's just to give you a flavor of the types of things that we sort of looked at in terms of really trying to deeply understand what the adversaries are doing. And of course, what we've got to do then is say, well, that's nice, but can we make it real? And I'm going to skip some of the nitty-gritty details of how we did that. But effectively, we worked very closely with folks in machine learning to design a classifier based on the features that I showed you and others to actually design a detection system that works well enough for people to actually use it. So I'm showing you here one point in an ROC curve. I'm picking the 70% detection rate because that's what state-of-the-art IP blacklists give you. For that point for that detection rate, we see about 0.4% of a false positive rate, which is actually too high Still too high to be used in practice. It's also too high for reviewers to accept your paper. So, so basically what we were able to, what we did then is actually play a bunch of games. You can turn a bunch of knobs, most of which that aren't that interesting, but involve a combination of whitelisting tricks, et cetera. You can get that down to about 0.1%, which is actually where people like McAfee and Yahoo will actually pay attention to you. So this is something that actually we showed to, we worked with McAfee on this. They took the features that we used and put them into their classifier. Yahoo actually also saw this work and said, hey, we want to, we also have some problems. Can you help us with those? And that's what I'm going to actually talk about next, which is a different kind of behavior, coordination. So here, we're talking about, well, spammers behave like each other. Can we use that somehow to our advantage? Well, everything I've talked about to this point is, still reliant on the fact that spam is coming from, distributed botnets, and, maybe we can detect things based on that. That's all changing, right? Everyone's using webmail. Right? So now IP addresses, everything that I've talked about, there's a danger of it all going completely out the window because everything's going from Gmail to Gmail. What does that mean? Well, it means that the webmail providers are increasingly reliant on these spam and not spam buttons that you see in your webmail client. So, of course, we can talk about spammers' coordinated sending behavior, but something that's more interesting that we could talk about is spammers' coordinated use of these buttons. Okay, so here's an interesting attack that we've discovered, is that spammers are compromising webmail accounts with weak passwords, right? And they're sending themselves mail. Okay, kind of weird. But what can you do if you send yourself spam? Well, you can actually then vote on it. You can say, you put that in the spam folder, bad mail filter. This is really not spam. Okay, well, this is a huge problem, right? Because false positives are just a disaster, right? So anytime someone clicks on this not spam button, the webmail provider treats that very seriously, right? So it only takes a few of these to really mess things up. So that's also a challenge, but going back to our axioms, right? We know spammers can behave in this in coordinated fashions, and if we can somehow pull out that coordinated activity, then maybe we can do something about it. And that's actually what we do. We actually, as I mentioned, sort of from the first part of the, from the very first slide, we reduce that sort of messy problem into something we can model, right? And what we do here actually is first, of course, first characteristic is volume, but the second is that spammer IP addresses, they receive a lot of votes, for not spam from many different compromised accounts. So how many times have you used this button? Probably not that frequently, right? But spammers tend to use it more than we do, and they tend to vote on, you'll see cases where a single compromised account, like as I've listed here in, or a single compromised account, which I've shown here in red on the left, might vote, or I should say multiple compromised accounts on the left might vote on a single IP address on the right in the same way. So what we can do then is cluster these red guys over here on the left, and those clusters tend to pop out. So that's the basic idea, is we just sort of use clustering and pop this out. So, and the strawman approach there is to just build like a k-neighborhood graph on this, and what you can do sort of if given a bipartite graph like that, you can build like 1 or 2 neighborhood graphs, but the problem with that is false positives. There can be some cases where for some particular reason, a user logs in from an IP address that is coming from a compromised machine or is coming through a proxy, and then just using a k-neighborhood graph actually tends to give you a too high of a false positive rate. I don't have time to get into all the details here, but essentially, again, what we did is work with some folks in machine learning. There's actually a well understood approach called canopy clustering, which is often used to make clustering of very large data more scalable. But another thing that it does as a side effect is give you some more control over sort of what operating point you choose in terms of false positive and detection rate. And sort of applying that, we were able to reduce the false positives that we see from a sort of basic k-neighborhood approach by about a factor of 10. And the detection rates in these cases aren't that high yet, but just keep in mind that these are instances of cases where before the mail providers had absolutely no idea of how to actually get these fraudulent voters in the first place. So this is something that actually we worked on with Yahoo. All the data that sort of drove this part of the work was done in collaboration with Yahoo, and this is something that they use in their mail filter today. So some ongoing work in this area that I'm looking at now is to sort of think about more axioms, right, and how we might use those to improve detection mechanisms. So one is that, as I mentioned already, spammers have to have a point of sale. So if you try this at home, you can sort of search for something, right, say Viagra, and you can sort of look around on the Washington site, and actually you see some things that freshman something program, and things that you wouldn't necessarily expect to be having material about Viagra on them. What's going on here? Well, actually, what's happening is that attackers are now compromising web servers that have vulnerabilities and using those sites as redirection points, right? So this is another example of, well, okay, this added point of indirection is annoying, but if we could somehow detect these, then again we could potentially stay one step ahead. So the challenge here is actually finding them, right? Because we obviously can't scan all web servers, and spammers cloak this activity, right? The scammers cloak this activity, so that if you just go looking for it from where you are, you might not see it, right? They only show it to you if you're coming from a particular referrer, from a particular subset of IP addresses, right? So actually finding out where these redirection points are is still, I think, a big unsolved mystery, and that's something that we're looking at. Jumping to the second problem that I promised to talk about is how we maintain openness in this battle for control. And I'm going to talk about a particular system that we've built to circumvent various types of censorship practices. So this is a pretty old problem, right? Censorship has been around pretty much since the days of communication. But in particular, it's as we've all observed, it's seeing increased relevance. So just to give you kind of a toy picture of what this looks like before jumping into the details, right? Alice wants to talk to Bob, and there's some firewall in between these two parties that's trying to prevent them from talking. And we typically call that party a censor, and that censor might block traffic, right? That's something that we all really understand. The other thing the censor might do is actually punish the user, right? And this, I think, is where things get really interesting, right? Because this is where we sort of divert from sort of a lot of traditional security and cryptography types of mechanisms, because if Alice could get in trouble for using something that gets around the firewall, that's sometimes even worse, right, than not being able to talk to Bob in the first place. So we're going to come back to that in just a minute. But before we come back to that, let's just talk about general approaches for solving this, right? And they all kind of look the same way. The general approach is to say, let's use some kind of helper, right? So even though Alice and Bob can't talk directly to one another, maybe Bob can talk to this helper, and maybe the helper can get through the firewall, on Alice's behalf. Typically, we think of this as, proxies or mixnets, right? So Tor being a prime example of this, but as we've increasingly seen, because it's fairly obvious when a user is using Tor, and it's also, not necessarily obvious, but we've seen sort of increasingly even in sort of very recent days, the censor themselves trying to seek out the location of these proxies and relays and block them, right? It's becoming increasingly important to not just hide what you're getting, right? Not just hide Alice and Bob's communication, but actually conceal the fact that they're communicating at all in the first place. So what we want to do, in addition to concealing this, concealing the contents of the communication, we actually also want to achieve a property called deniability, right? We want to basically make it such that it's hard for a censor to actually figure out that Alice and Bob are even talking at all. Now, so from here, again, we steal a lot of techniques from different areas of computer science and outside to sort of build a system that achieves these properties. So the censor, of course, could try to disrupt communication between Alice and Bob. So for that, we apply, various techniques to achieve redundancy and also message hiding properties. The censor could try to, uncover Alice and Bob as participating in something that's subversive, right? So we want to make things look as innocuous as possible. For that, we sort of, I'm going to show you how we construct traffic that looks as normal as possible. In this case, I'm going to steal some things from distributed systems. Finally, if the sensor can correlate somehow Alice and Bob's communication, then that's also a problem. So what we try to do is actually decouple the sending and receiving of messages. And here, I use a real-world analogy. So we can kind of think of like blind drops as the real-world analogy. Like if I want to leave a message, if I want to communicate with someone, I might not talk to them directly, but instead I might leave a message in a brown paper bag under a bridge or something and tell them to go there and pick it up later, right? So that's effectively what the system I'm about to show you does, except it does it in the context of user-generated content. So the idea here, by user-generated content, I'm specifically going to use Flickr and YouTube as an example. But we can think of this as any site out there where a user could post content. We're going to use that as our brown bag under the bridge. Right? So Bob is going to take some message that he wants to publish or send to Alice. He's going to embed that somehow in a picture or movie or what have you, and just put it up somewhere for Alice to snag. And Alice is basically going to snag that set of pictures or movies or whatever. To the sensor, this is going to look like Alice browsing a photo album or watching a movie. But in fact, what she really cares about is that yellow message that's sitting inside the content. OK, so one level deeper, how do we do this? Right? I'm going to skip a few steps, but I'll point out where the challenging parts are, of course. So Bob's going to take his message, and then Alice and Bob have to agree on what I call a message identifier. Now, this might be something like a URL, for example. So if Alice knows that she's looking for the front page of New York Times, that message identifier is easy, right? But if Alice and Bob need to, sort of send private messages to one another, they need to somehow bootstrap that step. Bob's going to take that cover media. He's going to somehow embed that message in the cover traffic. He's going to upload that to some site that Alice can also see, and then Alice is going to reverse that, right? She's going to download that content, and then she's going to extract the message. OK, so there are a few challenges here. Right? One is how to embed the message. Right? How do I do that in a way that it's difficult for the sensor to discover or disrupt it? How do Alice and Bob actually agree on where to put, where that drop site should be? Right? And how do they do that in a way such that Alice's process of retrieving it doesn't get her in trouble? And so these are the three challenges. I'm going to just sort of briefly highlight choices that we made in achieving those and solving those challenges. So in terms of embedding, here, of course, we can do some fairly straightforward things. If Alice and Bob have a message identifier, they can encrypt that message. They can erasure code that encrypted message, and then embed those chunks into the cover traffic using some fairly well understood either message hiding or watermarking techniques. And Alice and Bob's choice of whether or not to use things like message hiding, like steganography, or a sort of a robust watermarking technique really just depend on the type of properties that they want out of the system. I don't have time to really describe the nuances between that choice, but the bottom line is that either can work. Now, here's the fun part, right? Where to actually put this stuff, right? Alice, of course, can't crawl all of Flickr or YouTube or all the internet to find, where Bob dropped that message. So they've got to somehow agree on a subset of content that Alice should be able to crawl without immediately communicating to one another. So the solution here is to come up with some predictable way of mapping these message identifiers to some subset of hosts that might be hosting this user-generated content. And we want to do that in a way that's deniable. And the way that we do that is to take this message identifier, hash it into some ID space, right? So for those of you who've seen distributed hash tables, this is exactly that, right? So we take that and we hash it into a space. And then we also we have what we call sort of a list of tasks, right? A mapping of tasks. And these tasks are also going to map into that ID space. And these tasks are going to be things that we choose, right? That we define. But we're going to define them in such a way that Alice doing them is not going to get her in trouble, right? So searching for, looking at blue flowers on YouTube, or watching the latest, videos of cats, or whatever Alice might like to do in her spare time. So we, in essence, we create the mapping so that what Alice does doesn't get her in trouble, but still allows her to find that message in a reasonable period of time. Now, what do I mean by reasonable? This is not fast enough for, say, real-time Skype communication or even real-time chat. I mean, we're still talking about minutes, right? So in terms of challenges in this area, one of them, of course, is how do we design systems like this, to allow sort of more real-time communication? But I think that's just one of many challenges in this particular area. Just a few minutes on the very last, where I see this battle for control going, and that's sort of in maintaining transparency. In particular, one specific thing that I'd like to talk about is personalization, right? So increasingly, even in the best of scenarios, search personalization and various aspects of personalization on the web from many of our favorite services are restricting our view of what's out there, right? There's too much information, and we're really reliant on these personalization algorithms to help us winnow down what we see. Well, even in the best case, online personalization is creating situations where we're only seeing things that really already suit our own taste. Movies that we like to see, friends' status updates that that we're most interested in, books that we like to see, and so on and so forth. In the worst case, and I don't have time to describe this, but some recent work that we've been doing looks at how personalization can actually be vulnerability for an attack, right? So I can do things like if I want to make my web page come up first when you search for security, well, I can tell you how to do that later, but we know how to do that. So in the worst case, personalization can be exploited, right? So what can we do about this? I think this is a very rich area, and I only have a couple minutes, so let me just kind of give you a taste for the types of things that we're looking at here. One goal is to sort of increase transparency, right? So at least give the user some control back, right? And first, we can show them what they're missing, right? How do you do this? Well, let me just describe how we're doing it in one context, and that's in the context of web search, right? So the natural thing when you maybe search for something is to say, well, these are the results I'm getting, but how do they differ from your results, right? What are other people seeing? And the first thing you could do here is take that query, right, and execute it from different places and from different perspectives. And you might do that from different geographies. You might do that with users of different search histories. And then you can ask, what shows up on the first page? How does that differ from what other people are seeing? And maybe, eventually, we could come to a point where you could actually control that, right? You could say, I would like to query, with a certain persona. Right now, we're sort of just at the point of figuring out how to improve visibility for users. And I think there's some very interesting crossovers in this space with sort of visualization and HCI as well. But let's say, by the way, at the end of this slide, I'll give you the URL for this Chrome plugin. But let's say that I want to search for Arvind, right? Actually, what this plugin does, right, is when the search results come up, I see one thing. But I can actually ask this plugin, what else are other people seeing that I didn't see, right? So in yellow here, what we see are things that other people in other regions are seeing that didn't show up in my top 10. Right? And here I think I've hovered over one of these to sort of show, okay, this one is one that appears to be regionalized outside of the US. Right? So this is really just like a taste of the types of things that I'm really interested in looking at more. This is just how geography affects what we see, but also things like how do what you've searched in the past affect what you see, how do what device you're searching from, et cetera. I think there are many things to do here, both in terms of improving visibility for the user and in terms of giving control back to the user in terms of the information that they actually get. So you can actually try this out as well. This is a Chrome plugin that we've recently released. So just in conclusion, I've talked about many aspects of the battle for control and how we've kind of taken tools from different aspects of computer science to sort of bring back, to sort of engage in this battle with attackers, both in the context of message abuse, censorship, and now just briefly I've shown you how we can what we can do in terms of combating manipulation. Looking ahead and sort of going back to to my general approach, I just want to talk about just briefly about some other hard problems that I'm working on. Just sort of reminding you of the approach that I take, where I start from sort of things that require some deep domain knowledge and then bring to bear different aspects of computer science to solve those. So just to briefly touch on, here are some examples of other problems that we're looking at. So in particular, one that probably we've all experienced, right? Why is my network slow, right? Is it the fact that the home wireless network is just terrible, that my access point is behind a brick wall, or is it my ISP's fault? Pretty simple question, but actually we don't have a very good understanding of how to solve it. You can ask the same question, by the way, for mobile phones, right? And we're actually working now with Qualcomm and the FCC to work on a new study to sort of help users better understand what the performance of cellular networks is. We're also looking at questions about sort of how do we control propagation of sort of information that you store in the cloud. And one of my students who recently graduated has just started a startup in this space that just came out of the Y Combinator accelerator. Coming to that sort of softer question about sort of information and trust, there's another sort of interesting area that I've begun to look at, which is, we're very familiar with conventional notions of integrity, confidentiality, and so forth, but there are other scenarios where the sort of conventional approaches don't apply. So take, for example, a disaster scenario where a network doesn't exist, and then suddenly someone erects one. Well, you no longer have a public key infrastructure or certificate authority. When you get messages, how do you know whether or not to trust them? How do you know where they're coming from? How do you deal with prioritization, even in such of messages, in such a chaotic, unstructured type of network environment? So in order to solve these problems, actually, I'm engaging people from a much broader range of disciplines, and these are things that I really hope to work with you on as well. In particular, we're looking more at problems in the home networking space, as I alluded to, and those are things where, as I mentioned at the beginning, we like to work with network operators. In that case, the network operator is you, whether you like it or not, which means that we can't do that kind of work and achieve meaningful results without working with real users. So I'm engaging with people in human-computer interaction on those problems. Another one, if you sort of just look more at kind of bigger networks where network operators are configuring big Cisco and Juniper routers, et cetera, we're still in the age where configuring big networks like that is sort of in the analogy of sort of like assembly language, right? So how do we basically design networks so that they're much easier for people to program? And here, the insight that I'm building off of is that network configuration really should be a description of what should the network do in response to a particular event. What should happen when an intrusion occurs, for example? Well, there are natural things in programming languages like functional reactive programming that are very good at describing that type of thing, and I'm working with people in that area to help solve those kinds of problems. Network pricing is another one. So, for example, the last mile isn't typically getting any fatter, but the types of things that we like to push into homes in over-the-top video are just getting bigger, right, and more. Can we use pricing and incentives to get people to do demand-side management and get people to sort of shift what they do or when they do it? And finally, I know there's a lot of work going on in the ubicomp area here in terms of behavioral sensing, and that's also something that we're starting to look at more. Can we use network traffic collected from home routers as an indicator or as a signal for whether or not people are home, whether or not they're awake or asleep, and so forth? Okay, so just to kind of wrap up, I like to ultimately have impact beyond the research lab, and I aim to do that in many different ways. And here are just some examples, just through outreach, for example. I view education, I take it very seriously, and one of the things that we've done in the classroom is to sort of redesign the networking course to have sort of a more hands-on feel, and there's a paper that I wrote describing that's in the SIGCOMM education workshop last year. I spent a lot of time in the talk talking about tech transfer, and also, where appropriate, we've tried to commercialize some of the aspects of this research. So that's all I have for you today, and thank you very much for your time, and I'm happy to take any questions if there's time remaining.